Let me see whether I can use a point. Alright. Alright, let's get started. Good morning everyone, thanks for coming. I'm going to talk to you about new ultra-trace level silica analyzer for power plants. Trying to get used to this, looks like it's not going to turn, so I'm going to use the computer. Okay. So first I'm going to introduce you the silica background and why do we care about it, why is it important to monitor silica in power plants and more. And then I will talk about what are the challenges we have in analyzing silica in power plants operation. And then I'm going to introduce you to a new solution, which is a new online silica analyzer. And then I'll talk about a few case studies where we actually installed and tested this analyzer in a few power plants and ultra pure water facilities. Okay. Alright, so what is silica? Typically, when we talk about silica in power plants, we refer to silica dioxide, especially the reactive silica that's kind of soluble in water. It's in your boiler water, feeder water, it's in your DI water, steam condensate, or permeate, and that may bring you problems for scale, heat exchangers, in your turbines or deposit, as you can see in some of the picture here. Severely clogged will kind of reduce your heat exchanger efficiency or cause maintenance issues for you. So we do want to avoid it, and the best way to avoid it is to monitor the silica level in your water in real time online, so that you can see, hey, I have more silica that's over my threshold, give it 15 or 20, whatever your plant's guidance is, to reduce it down, or to recycle that water, or change your water treatment operation so that you can keep it under your desired limit. So which industry need to monitor silica? Obviously power plants and some ultra pure water facilities. There are more, but we don't need to talk too much about it here. Alright, so another example of how silica would damage or can hurt your power plant operation. As you can see, all the wide scale forms on this turbine, even just after 3 months of operation of this new turbine is installed. This is caused by inadequate steam water separation. So some of the water with silica get into your steam, and then eventually when they evaporate, they precipitate and forms a deposit on your turbine. And this is definitely, you have to shut down, you have severe maintenance and cost, all that. You don't want to deal with it. So in order to avoid an incident like this, what do you do, right? We want to put silica analyzer, like online silica analyzer, after you treat the water through your water treatment facility or water purification, DI plants, whatever, dimming plants, whatever you call it, to your makeup, right? You want to see, hey, how much water is coming to my makeup. You also want to see how much water is going to your turbine. Maybe some in the middle of the process, maybe something changed, right? During startups, you could cause turbulence, kind of disturb some of the silica scale in your feed lines and to your turbine feed wall. So you want to monitor somewhere here too. You also want to monitor what's in your condensate. And maybe there's some like what this instance is. Maybe some water got into your steam, and you can see that from a condensate by monitoring there. So so all this can, obviously some of the steam condensate goes to the makeup. So all this is sources of your silica, and by monitoring it in different places, you will be able to see exactly where they come from and have a correct response for it, because obviously you need different response if it's coming from different areas. So just kind of re-emphasize, right? Your heat exchangers can get clogged like that if you don't monitor, and especially for power plants, right? If you form just maybe 1 millimeter of scale, you could easily reduce your heat exchanger efficiency by 30%. That's a big drop in your power generation. and also high kind of maintenance cost as well. It's also a good indicator, in your dimming plants, in your deionized water plants, to monitor silica, because as the ion exchange resin gets saturated, silica is typically the first one eluting from the ion exchange resins. So you will say, hey, I need to change my ion exchange resins. Maybe, hey, similar for its RO, if you have a breakage, whatever, you could see that, firsthand, and then you can change your water treatment system to avoid this or reduce your silica down. Okay, so what are the common kind of challenges of silica analysis in power plants operation? So as we know, right, there are typically two types of plants. One is the base load plants, which is on continuously, and there are picker plants, which is on, kind of we say turn on demand, when it's peak season in the summer or in winter, whenever it's needed, you turn it on. But the picker plants, there are a lot of picker plants here, right? So what do? We have to start up and shut down that picker plants quite often, which means you have intermittent flow condition. During startup, you suddenly increase the flow, and that could cause this turbulence and scraping off some of the particles, silica deposit, ion deposit in your pipes, and that causes your system has a lot of silica. So you want to avoid that. And in the initial stages, how do you treat it, how do you analyze it, is critical. You don't want to risk of damaging your downstream operation if you're not catching these events. So that's why we need to monitor it, and it presents pretty good challenge for silica analysis as well. The analyzers don't like to see a lot of solids coming to the system because it may clog it up. So this is a potential of clogging the sample tube. Also, because our picker plants is on and off, sometimes it's even off for maybe weeks, months. We want the reagent to be really stable because we may not use it for a while. We want the reagent to be, still, in liquid form, not crystallizing, not precipitating on your sample tube, on your reagent line, so that it's not going to be good anymore after you come back to operation. So these are the challenges it has for our reagents. So in our research, we optimize this reagent formulation to deal with this, which I will talk about in the next few slides. Another major issue is the phosphate interference. Some of the plants, as we know, right, it uses phosphate as a corrosion inhibitor. So phosphate acts pretty similar as silica, so it will react with the reagent and forms a color, which will be detected by the analyzer. So we want to minimize the impact of silica interference. Right, so what we do here is obviously optimize the reagent to be really stable. We follow the standard method, and but we optimize the reagent in a way where it's stable and deal with the phosphate interference. So what we do is the first reagent is a color reagent. It forms a complex, the molybdenum silicate acid with the silica. So it also forms a phospho-molybdate complex. Both of them will show as a kind of yellow color here. So to deal with the phosphate interference, right? We don't want to measure any phosphate. We use a masking reagent that will break off, destroy the phospho-molybdate complex, and then we use a reducing agent to turn the remaining molybdenum silicate. It's hard for me to pronounce it, but anyway, this complex to blue form, which is what will get measured and is correlated to the concentration of silica present. So, and after that, right, we tested how good is our newly formulated, optimized reagent. We compared it with some of the competitive reagents. Initially at a fresh solution, they will measure at 1.3-ish absorbance. But after a week, you see some competitive reagent they could degrade, measure down to 0.98. Right? That's about 25% of decrease in absorbance, which means in the response. But in our reagent, we keep it pretty stable. Even after 5 months, it's still 1.3. So 0.7 only change. So that's one kind of improvement we did, right? Kind of extend the stability over 5 months, actually over 6 months, no problem. And another thing we tested is phosphate interference. For plants that use phosphate as corrosion inhibitor, sometimes they use it at 10 ppm, few ppm. But for one of the competitive analyzer, we see that even at 1 ppm, right? We add 1 ppm phosphate into 20 ppb of silica standard, it's measured 56 ppb. So that's 36 of measurement error. So you don't want this, right? It causes measurement error and false alarms for high silica events. So in our event, right, we add in our new analyzer 8030, we add 30 ppm of phosphate, way more than what you would even expect in your system, into the 20 ppb of silica standard. It's measured 23, only 3 ppb increase. If we add at this level, it's pretty much nothing. It's measuring 20.5, 20.8. So that's why we give it extreme condition to test. It's still kind of acceptable. So this shows that our optimized reagent is able to handle phosphate interference much better. So as we discussed, right, pickle plants, intermittent flow. So what do we do to deal with that? So we have a smart sensor that detects, do we have sample water? Right? If we have sample water, you will resume, operation. But if you run out of sample water, then the analyzer will shut down by itself, because the smart sensor, flow sensor, will notice, hey, there's no flow coming. I don't need to analyze. I don't need to waste my reagent. Everything is automatic, and it will give you an alarm like this. Hey, you have lots of flow. If the operator says that, oh, maybe I forgot to turn on the valve on during startup, so he will correct that, right? Well, in normal cases, if it's just no shower down, this will be just, hey, you're shutting down mode, right? Lots of flow. Gives you clear indication. It will also give you some warnings too. If you set up alarms like, hey, anything over 15 ppb, send me an alarm. Like, we can set it up in the analyzer to say, hey, display it on my screen, send it to DCS system or PLC, whatever you like, wherever you want to see it. And if it's reagent low, hey, I want to know, right? Operator want to know, so I need to order reagent. It will show that too, whatever alarm you like to see. Another major issue, as I mentioned, right? Sometimes the pickle plants would shut down for a period of time, weeks for maintenance, even for baseload plants. Every year, right? October, whatever, you gotta shut down for a month. To maintain your system, and the analyzer will be down for a month. In a lot of analyzers, the reagent would crystallize because there's no water anymore, right? They form solids on your sample tubing, on reagent tubing, and that prevents you from resuming the operation. That's a major issue for a lot of these analyzers. In this new analyzer, what we designed is we have a smart system. So first, it has auto cleaning. Every time if you haven't run for a long time, you will start auto rinsing, auto cleaning. So start injecting water, injecting cleaning chemical, make sure it's clean. And in addition to that, we have a smart way to make sure we're not leaving the reagent in the sample line, so it does not get crystallization or solids forming in your sample line. So what we do is, after you not analyzing for a few hours, you push the reagent back to the reagent bottle, so you don't have any reagent in the sample line. When you are shut down for like weeks or periods. So in this case, everything is safe, and when you restart, start auto cleaning, auto rinsing, everything is back to normal. You don't need to worry about, oh, my analyzer is not working anymore. So I want to talk about a little bit more of technology inside this analyzer. So first, we used a kind of four-side cuvette. It has a coarse cell, basically. It has a short side and it has a long side. For a low concentration, typically like 0 to 20 ppb, you want to measure at long patterns that gives you higher signal, and then give you lower detection limit, right? So that's how we measure it, between say 0 to a few hundred ppb. When you are sometimes, in your boiler sludge measurement, other silica measurement, if it's a geothermal plant, they have high silica too. So you would use the short patterns to measure higher silica concentration. And that's converted automatically in the analyzer. You don't need to worry about it. It just calibrated this at the start. So the analyzer is smart enough to choose which patterns I'm analyzing based on the concentration you're detecting. Another thing is the patented fluidic and analytic process I want to talk about. We have a special liquid sensor here, and we have special way to analyzing to maintain the accuracy of the volume we are using, volume of the reagent, volume of sample. Typically in some analyzers you will say, hey, they use peristaltic pumps to quantify. 3 cycles, that means 0.6 milliliters or whatever, but the pump's age, the pump's kind of wears down, right? So initially you're getting 0.6, now you're getting 0.5, 3 months later you're getting 0.3. So that's an issue a lot of the analyzer is facing. In our case, we're not using the peristaltic pump to quantify how much water, how much reagent we are taking in. We only use it as a way to get water, basically a pressure kind of device. So what we do is we take sample in by switching a Yardley valve into multi-way valve instead of using multiple single valves. So the sample will come in through the Yardley valve and this line to the liquid sensor. The pump is just a way to get water through, and then once the sample reaches sample line, it goes to clean waste. Basically, it's just a rinse. Okay, you can discharge it anyway. So this is the section of the sample. The liquid sensor tells us, hey, this is a flow of liquid, and here between here and here is where it determines how much liquid we are sampling, rather than relying on the pump, where the pump can deteriorate over time. So this tells us always we're sampling, say for example, 5 milliliters of liquid, because it's the section of tubing. The section of tubing never changes. Similarly, we do it for reagent. We're sampling, for example, 0.2, 0.1 milliliter of reagent. We use a smart sensor again together with a section of tubing to determine how much we're sampling. So this way we improve the accuracy of sampling volume down to 0.1%. If you're using pump, the sampling accuracy can be 5%, sometimes 10%. So that's a major issue for your measurement inaccuracy. Obviously, after that, we switch the valve, and then we using the air pump to push it back. Pumps are just devices to push water and getting water, rather than quantify the volume we are using. So that's a long story short how we design the system, and we have a pattern on this system. With all these kind of features, right, we were able to achieve superior analytical performance down to 0.5 ppb and 1% error wide analysis range. You can tolerate 30 up to 30 ppm of phosphate, and really you don't have to maintain it for the operators, because they can really focus on more value-added tasks rather than, hey, keep to maintain or calibrate the system. Because this analyzer can do automatic measurement. You can set it at an interval, calibration at an interval, validation at an interval. Calibration means, hey, this month I calibrate at this day, this time, and then validation is, hey, I want to make sure my calibration is still good, right? So I can validate every 3 days, every week, whatever you want to validate. And that gives you, oh, okay, maybe 3 weeks later or a month later, my calibration drifted. I need to recalibrate. You can look at the validation log and say, hey, this period of time, my data is drifting off by 1 ppb. And then you can correct for that too. So all these are nice features that we enabled with our analyzer. And we use the 7-inch touch screen as a user interface. It's kind of like a smartphones, right? Instead of understanding what's the complex menu, which button to hit, it's really obvious. Everything is graphic. Calibration, validation, measurement, setup. You can set every few hours, measure once, and then what alarms you want to set. You can look at calibration logs. When was the last time any operator calibrated? When was the last time you analyzed? It has all this data logged. And it has a IP65 metal enclosure. It's very robust, and it can withstand weather and moisture. For data output, we allow Modbus or analog 420. Either way, whatever you prefer, we can provide. And there are more communication protocols we can support too. We just did not list it here. So going to the details, what does the analyzer screen look like? Right, it will look like this. It has when everything is good, it shows a green heart. When something is giving you alarm, for example, my silica level goes above 20. I want to show yellow, whatever. You can see that, right? Operator passes by. Oh, that's yellow. I need to take a look at it, and it will tell you which process it is. Am I in cleaning? Am I in validation, measurement? It has process bar. How long does it take for me to finish it? Everything is very clear. And you can look at, you can go to logs. You can look at, hey, what was the last time it was calibrated? What was the factory calibration? How much difference are they? Obviously, if someone messed up, you can clearly see factory calibration slope was 100, and now you're getting only 20. That means probably something messed up, right? So that will give you a track record of fixing the issue rather than, hey, worry about what went wrong. Yeah, all the data logs are there. You can look at, past 3 months of data, 6 months of data. The data are supposed to be good for a year. So anything you want to trace back, can trace back. And it has, as I said, automatic features that really help the operator, kind of have peace of mind. They don't need to worry about, hey, I need to validate it, every 3 days, or I need to clean it every week, whatever. It does it automatically. You just need to set up interval. It runs automatically. Okay. So going back to how does this analyzer address the challenges in power plant? I kind of connected, but this is a kind of a summary, right? Intermittent flow, we have automatic sampling and shutdown, right? When the sensor senses the flow is coming in, the analyzer start measurement. When the sensor sees, hey, there's no liquid coming in, the analyzer stops, pops alarm. You don't have flow. And particle in sample, we have smart feature to auto clean and rinse before we do measurement. And phosphate interference or optimized formulation, so that you can do up to 30 ppm of phosphate. Reagent stability, we formulate it in a way that it can last over 3 years on shelf, and in the lab we tested it more than 6 months. When it's open to atmosphere and in your actual customer site. Reagent crystallization, as we said, pushing in, push back, using smart features that avoids any reagent precipitation or crystallization in the tubes. Further accuracy, right? Accuracy we achieve through design the way of quantify the volume of intake using the liquid sensor and its fixed segment of the tubing. This way we achieved like 0.1% of volume quantification accuracy. And we also optimize reagent so that it has a higher signal. Environment temperature fluctuations. Sometimes your analyzer is in your shed. It's not a temperature control. You don't need to worry about it. Sometimes even you run cold water we have temperature control reaction cell that brings up the temperature always to fixed temperature. This allows stable reaction and also consistent reading from time to time, from winter to summer. Contamination. Some analyzers would have carryover effect, especially for analyzers that are using peristaltic pump, one flow in, one flow out. Our system is designed that it takes the last little drop of analyzer from of the reaction liquid from the reaction cell, because we take it out from the bottom. We have angle shape. Some of the analyzers like, hey, coming in here, coming out here, there's always a residual layer in the reaction cell that causes you know, like 5% error in your carryover. Reagent deterioration, we showed you data that after 6 months we are still good, only 0.7% change in your absorbance. If you need to measure multiple sample stream, we have designed a sequencer that goes with this analyzer. You just put it integral to the bottom of the analyzer. It's a small case, and everything can controlled by the screen. Just like you know, your phones, you add this additional app, you can still work on it. It's easy to operate. You don't need to buy additional analyzer. You know, you can operate up to 6 streams. Right. So here I'm going to show you some interesting case studies. We did put this analyzer in 3 power plants and 1 pure water facilities. And here are the installation pictures. And here's 1 power plant in New Hampshire. So what we did is we installed after in the effluent end of the dimming plant, and the customer definitely wanted lower than 20 ppb, 20 milligram per liter. Sorry, microgram per liter. And typically they actually want it to be, you know, kind of ideally less than 15. So when they measure it, sometimes they're above this 15 target, right? And in this case, they look at their system. Hey, I need to recycle my water. I need to change my dimming plant operation to drop it down. So enable them to, you know, switch or optimize their water treatment operation properly. So in this case, we monitor here over 3 months. Everything is show that, including the validation data. So we validate every 2 days to say, hey, you know, we're gonna measure a standard bottle. We put it in every 2 days, and it's this 20 ppb. What's our measurement data? It shows 20.1, 20.3, 17.9. Everything is good. See here, within 1 ppb, right? Very clear. That shows that our analyzer is stable, able to, you know, kind of run stably over 3 months, giving different temperature swings, different temperature changes. It's within the spec of 1 ppb error or less. We also did standard recovery test. In standard recovery test means, you know, we have different sample water from the site. We spec in, for example, 5, 10, 15, 20 ppb, and how much we are measuring in addition to the sample water background. And you can see we typically get 99% to up to 1.3 or 103% kind of recovery. So pretty good, right on the spot. Here's another power plant we ran this analyzer at, and you can also see, you know, validation. It's generally pretty good. We choose a different validation. This time we chose 200, just give it a different switch. You know, variance is typically within 3%. And occasionally they do have, you know, they also get kind of one below 15. That's ideal, because 20 they definitely don't want to exceed 20, but 15 they give them a good buffer. So every time when they exceed, they can see that from the analyzers. They can take proper action right away. You know, say divert water, recycle, or try to improve their operation. Maybe their RO or their ion exchange resin need to be swapped. So it's a good indication for them to look at those things. We also did a standard recovery test here as well. Showed a pretty good results. Here's another example. This is a dimming plant specifically, and so we sampled the effluent. Again, their target is less than 20, but they are pretty good in treating their water. So they're generally below 4 ppb. Kind of shows how accurate we are in the analyzer, right? You can detect down to 2 to 3 ppb pretty accurately, consistently over a few months. So after deploying this analyzer, the customer is really excited, and they want to take our analyzer. Yeah, with that, this is everything. Any questions or comments? Okay.
Is this used in any other use cases in power plants?
Any other use cases in the power plant?
Like other than power plants?
Yes, we do have. We use it in, for example, oil and gas has cogen plants. It's also providing power for them, but we call it cogen plants. You know, silica also is commonly monitored in if we go back in the semiconductor, they want to monitor whether silica can deposit on their wafers, and we're testing in semiconductor plants as well. So those are the things that you know that they care about. So I think probably in one of the slides I have it. Yeah, yeah. Some manufacturing do it too. Pulp paper, they also have cogen plants. Typically provide power for that plant, but it's part of pulp and paper. Any other questions, comments? All right, thank you. Are you leaving right away?
No, I think I'm gonna walk the floor right now one last time. And, oh, it's late. It's at like 6:30, but.
Oh, so you get there by 10:30.
Oh, no, I'm.
You're not going to Boston.
Oh, you need to get back to
Yes.
Boston? Yeah, I have like a connecting thing too, so I'm gonna get back at like 1 a.m.
Yeah, that's why I decided to do next day.
Yeah.
I thought about it.
Exactly. Yeah, but I have stuff to do on Friday. So. Yeah, definitely. Yeah, it was a good presentation. Yeah. Yeah, I don't know if they're recording or something. I'm gonna go check right now if there's a recording.